Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 1512, number of good pairs. This is a fun and straightforward problem where we need to count specific pairs in an array based on their values and indices. Let's dive in and explore how to solve it. In this problem, you're given an array of integers called nums, and your goal is to find the total number of good pairs in the array. A pair, I, j, is considered a good pair if two conditions are satisfied. First, the elements at indices I and j are equal, meaning nums, I, equals nums, j. Second, the index I must be less than the index j. So, we're essentially looking for pairs of equal elements in the array, but only where the first occurrence comes before the second. The input is a single array nums containing integers, and the output is a single integer representing the count of good pairs. Let's dive into some examples to understand this better. Consider the first example where the input array is nums equals 1, 2, 3, 1, 1, 3. The output for this example is 4, because there are 4 good pairs in the array. These pairs are 0, 3, 0, 4, 3, 4, and 2, 5. Let's break this down. For the pair 0, 3, the value at nums 0 is 1, and the value at nums 3 is also 1, so they are equal. Furthermore, the index 0 is less than 3, so this is a good pair. Similarly, 0, 4 is a good pair because nums 0 and nums 4 are both 1 and 0, 4. The same logic applies to the other pairs 3, 4, where nums 3 equals nums 4, and 2, 5, where nums 2 equals nums 5. Adding up all these pairs, we get a total of 4 good pairs. Now, take the second example where the input array is nums equals 1, 1, 1, 1. Here, every pair of indices, I, j, where I less than j forms a good pair, because all elements in the array are identical. The output is 6, and the good pairs are 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3. For instance, 4, 0, 1, both nums 0 and nums 1 are 1 and 0, 1. The same reasoning applies to all the other pairs. In general, when all elements in the array are the same, the total number of good pairs can be calculated using the combination formula nc2 equals n asterisk, n1/2, where n is the length of the array. For this example, n equals 4, so the total is 4*3/2 equals 6 good pairs. In the third example, the input array is nums equals 1, 2, 3. Here, the output is 0 because there are no good pairs. Since all the elements in the array are distinct, there are no indices I and j such that nums, I, equals nums, j. Without any matching elements, it's impossible to form a good pair, so the result is simply 0. Finally, let's consider some constraints and edge cases. The array length, nums.length, is guaranteed to be between 1 and 100. Each element in the array, nums, I, is also between 1 and 100. For very small arrays, such as when nums contains only one element, it's impossible to form any pairs because there aren't two indices to compare. In this case, the result will always be 0. On the other hand, if the array contains all identical elements, the total number of good pairs can be calculated using the formula for combinations, as we discussed earlier. These edge cases help clarify how the problem behaves in extreme scenarios, ensuring our solution works for all valid inputs. To solve the problem of counting good pairs, we need to focus on identifying pairs, I, j, in the array where the values at those indices are equal, and the first index is smaller than the second. The most straightforward approach is the brute force method. Here, we use 2 nested loops to compare every possible pair in the array. The outer loop fixes an index I, and the inner loop checks all indices j where j is greater than I. For each pair, we check if the values are equal, and if they are, we increment a counter. While this approach is conceptually simple and easy to implement, it has a significant downside. Due to the nested loops, the time complexity is quadratic O(n squared, which becomes inefficient as the array size grows. This makes the brute force method impractical for large inputs, despite its simplicity. Additionally, it uses no extra memory, so the space complexity is O(1). This trade-off between simplicity and efficiency prompts us to explore more optimized solutions. To improve on the brute force approach, we can use a frequency-based method that eliminates redundant comparisons. The key insight here is that if a number appears multiple times in the array, the total number of good pairs it contributes can be calculated directly using the formula frequency asterisk, frequency 1/2, where frequent is the frequency of the number. To implement this, we can use a hash map to store the frequency of each number as we traverse the array. In the first pass, we populate this frequency map. Then, in a second pass, we calculate the total number of good pairs for each unique number using the formula and sum these values. This approach is significantly more efficient than brute force, with a time complexity of O(n), since we only make 2 linear passes through the array. The space complexity is also O(n), as we use the hash map to store frequencies. By avoiding unnecessary pairwise comparisons, this method is much faster for larger arrays. However, there is still room for further optimization by combining the 2 passes into one. An even more efficient approach combines frequency counting and pair calculation into a single traversal of the array. This is achieved using a hash map to track how many times each number has been seen so far. As we iterate through the array, for each element, we immediately calculate the number of good pairs it forms with all previous occurrences of the same value. This is simply the current frequency of the number in the hash map. We add this value to our result and then update the hash map to reflect the current occurrence of the number. This approach achieves the same result as the 2-pass method but eliminates the need for a second traversal. The time complexity remains O(n), as we still process each element once, and the space complexity is O(n) due to the hash map. The key advantage of this single-pass method is its streamlined efficiency, as it minimizes redundant operations and calculates the result on the fly. The single-pass approach with a running count is the most efficient solution for this problem, which is why it is our chosen strategy. By combining frequency counting and pair calculation into a single traversal, it minimizes computational overhead and achieves optimal performance in both time and space. The brute force approach, while straightforward, is computationally expensive with its O(n)² complexity, making it impractical for larger inputs. The 2-pass frequency count method is a significant improvement, but it still involves 2 separate traversals of the array. In comparison, the single-pass approach achieves the same result with fewer operations, making it the most streamlined and efficient solution. While the single-pass method is slightly more complex to implement than brute force, it strikes the best balance between simplicity and efficiency. This makes it the ideal choice for solving the problem, particularly when working with large arrays. In this problem, we are tasked with finding the number of good pairs in a given array. A good pair is defined as a pair of indices, I, j, where the values at those indices are equal, and the first index I is smaller than the second index j. To solve this, we can start with a brute force approach that involves checking all possible pairs of indices in the array. First, we initialize a variable called count_0, which will be used to keep track of the number of good pairs. Then, using 2 nested loops, we generate all possible pairs of indices. The outer loop iterates over the array using index I, while the inner loop starts from I+1 and iterates using index j. For each pair, we check if the values at nums, I, and nums, j, are equal. If they are, we know this is a good pair, and we can increment our count. While this approach is simple and intuitive, it becomes inefficient for larger arrays because it involves comparing every possible pair of indices. Once we have identified a pair, I, j, where nums, I, equals nums, j, we increment the count variable by 1. At the end of this process, after all pairs have been checked, we can return the value of count as our result, which represents the total number of good pairs in the array. This brute force approach can be implemented in Python using 2 nested for loops. As shown in the code snippet, we initialize count_0 and iterate over all pairs using indices I and j. For each pair, if nums, I, equals nums, j, we increment count. Finally, we print the value of count, which in this example yields an output of 4, meaning there are 4 good pairs in the array. While this method works, it is computationally expensive. The time complexity is O(n)² due to the nested loops, and although the space complexity is O(1), since we don't use any additional data structures, this approach fails to scale efficiently as the array size grows. The inefficiency of the brute force approach stems from the fact that it explicitly checks all possible pairs, leading to a time complexity of O(n)². To optimize this, we can use a hash map to track the frequency of each number in the array as we iterate through it. The key insight here is that if a number appears frequency times in the array, it can form frequent asterisk, frequency 1/2 good pairs. This formula comes from the mathematical combination formula for choosing two indices out of frequency occurrences. By leveraging this insight, we can avoid the need to explicitly check all pairs. The optimized solution involves initializing an empty hash map to store the frequency of each number as we process the array. As we iterate through the array, for each number, we check if it already exists in the hash map. If it does, the value associated with that key tells us how many times the number has appeared previously. This count directly contributes to the number of good pairs, and we add it to our result variable. After counting the good pairs contributed by the current number, we update the frequency of that number in the hash map by incrementing its count. Once we finish iterating through the array, the result variable will hold the total number of good pairs, and we can return this value. The Python code for this optimized approach is concise and efficient. We initialize the count variable to 0 and the hash map as an empty dictionary. For each number in the array, we check if it exists in the hash map. If it does, we add the current frequency of the number to count, because that frequency represents the number of good pairs the current number can form. Then, we update the hash map to reflect the new frequency of the current number. At the end of the loop, the result stored in count gives us the total number of good pairs. This approach significantly improves performance by eliminating the need for nested loops and directly leveraging the hash map for efficient frequency counting. The optimized approach has a time complexity of O(n), where n is the length of the array. This is because we only iterate through the array once, and hash map operations like lookups and updates are O(1) on average. The space complexity is O(u), where u is the number of unique elements in the array, as the hash map stores the frequency of each unique number. Comparing this to the brute force approach, we can see a clear improvement. Instead of checking all pairs explicitly, which takes O(n²) time, we use mathematical insights and a hash map to determine the number of good pairs in linear time. This optimization highlights the importance of selecting the right data structures to improve algorithm efficiency. The hash map allows us to keep track of the frequency of each number and calculate the contribution of each number to the total count of good pairs in constant time. Additionally, we must consider edge cases, such as when the array is empty or when all elements are unique, in which case there are no good pairs. If all elements are identical, we can use the combination formula to calculate the result directly. When dealing with edge cases, if the array is empty, the function should return 0 since there are no pairs to check. In the case where all elements are unique, no good pairs can exist, so the output is also 0. On the other hand, if all elements in the array are identical, we can use the formula n*(n1/2) to calculate the number of good pairs, where n is the size of the array. This is because every pair of indices in such an array forms a good pair. The hash map is a powerful data structure that makes this optimization possible. By storing the frequency of each number, we can efficiently count and update the number of good pairs as we process the array. Overall, the optimized approach reduces the time complexity from O(n²) to O(n), making it suitable for large arrays with up to 10,000 elements. It demonstrates how combining mathematical insights with efficient data structures can significantly enhance algorithm performance, turning an otherwise impractical solution into one that is both efficient and scalable. This implementation solves the problem of counting good pairs in an efficient manner using a frequency dictionary. First, we initialize two variables, count to store the total number of good pairs, and frequency as an empty dictionary to keep track of how many times each number has been seen so far. The algorithm iterates through the input list nums. For each number in the list. If the number is already in the dictionary, it means we have seen this number before. In this case, the number of good pairs for the current number is equal to its frequency so far, i.e., frequent number. We add this count to the total count. Regardless of whether number was already in the dictionary or not, we update its frequency in the dictionary. If it was already present, we increment its count by 1. If it is a new number, we initialize its frequency to 1. This solution efficiently counts good pairs in a single pass through the array, resulting in an O(n) time complexity, where n is the length of the input list. This is a significant improvement over the brute force approach, which would require O(n²) time for comparing all pairs. The algorithm handles edge cases such as an empty list or a list with no duplicate values gracefully, as no duplicates will result in count remaining 0, and the frequency dictionary will simply track all unique values in the array without issue. This is the Java implementation of LeetCode problem number 1512, number of good pairs. The logic mirrors the Python solution, with a hash map used to track the frequency of each number as we iterate through the array. When a number is encountered, we calculate the count of good pairs by adding the current frequency of the number to the result. Key differences include Java's explicit type declarations and the use of hash map instead of Python's dictionary. The solution maintains O(n) time complexity due to the single traversal of the array and efficient hash map operations. To solve this problem, we need to count the number of good pairs in the given array, where a good pair is defined as two indices, I, j, such that the elements at those indices are equal, and I is less than j. For example, given the input nums equals 1, 2, 3, 1, 1, 3, we aim to compute how many such pairs exist. We start by initializing two variables, count, which will store the total number of good pairs and is initially set to 0, and frequency, an empty dictionary that will help us keep track of how many times each number has been encountered so far. In the first iteration, the number 1 is encountered, and since it is not yet in frequency, we add it with a value of 1. At this stage, no good pairs can be formed because this is the first occurrence of 1, so the count remains 0. In the second iteration, we encounter the number 2. Since 2 is not in frequency, we add it with a value of 1. Again, no good pairs can be formed yet, so count remains 0. In the third iteration, we encounter 3. We add 3 to frequency with a value of 1, and just like before, no good pairs can be formed, so count stays at 0. Now, in the fourth iteration, we encounter 1 again. This time, since 1 is already in frequency, we add the current frequency of 1, which is 1, to count. This means we have identified one good pair so far, and count becomes 1. We then increment the frequency of 1 in frequency, making it 2. In the fifth iteration, we encounter 1 again. Since 1 is in frequency, we add its current frequency, which is 2, to count. This brings count to 3, as we have identified 2 more good pairs involving this instance of 1. We then update the frequency of 1 in frequency to 3. Finally, in the sixth iteration, we encounter 3. Since 3 is already in frequency, we add its current frequency, which is 1, to count. This brings the total count to 4, as 1 more good pair involving 3 is identified. We then increment the frequency of 3 in frequency to 2. At the end of all iterations, the final value of count is 4, which is our output for this example. Now, let's consider another example where the input is nums equals 1, 1, 1, 1. We begin by initializing count to 0 and frequency to an empty dictionary. In the first iteration, we encounter the number 1. Since 1 is not in frequency, we add it with a value of 1. At this stage, count remains 0 as no good pairs can be formed yet. In the second iteration, we encounter 1 again. This time, since 1 is already in frequency, we add its current frequency, which is 1, to count. This gives us a count of 1. We then increment the frequency of 1 in frequency to 2. In the third iteration, we encounter 1 again. We add the current frequency of 1, which is 2, to count, bringing count to 3. We then update the frequency of 1 in frequency to 3. In the fourth iteration, we encounter 1 once more. Since 1 is in frequency, we add its current frequency, which is 3, to count. This brings the total count to 6, as all pairs formed by this one with the previous occurrences are good pairs. We then increment the frequency of 1 in frequency to 4. At the end of all iterations, the final value of count is 6, which is the number of good pairs in this example. Now, consider the input nums equals 1, 2, 3. We initialize count to 0 and frequency to an empty dictionary. In the first iteration, we encounter the number 1. Since 1 is not in frequency, we add it with a value of 1. At this stage, count remains 0 as no good pairs can be formed. In the second iteration, we encounter the number 2. Since 2 is not in frequency, we add it with a value of 1. Again, no good pairs can be formed yet, so count remains 0. In the third iteration, we encounter 3. We add 3 to frequency with a value of 1, and as before, no good pairs can be formed. This means that at the end of all iterations, the total count is still 0. The final output for this example is therefore 0, as there are no good pairs in the input array. To analyze the time complexity of the given solution, we start by looking at how the operations are structured. First, we initialize a variable count to 0 and create an empty dictionary called frequency. These are simple operations that take constant time, or O1. Next, we iterate through the array nums, which contains n elements. Since the loop processes each element exactly once, the iteration step has a linear time complexity of O(n). Within each iteration, we perform dictionary operations. When we check if an element exists in the dictionary using the in operator, the average lookup time for dictionaries is O(1). If the element is found, we update count and increment its frequency in the dictionary, and these updates are also O(1). If the element is not found, we add it to the dictionary with a frequency of 1, which is still an average O(1) operation. This means that each iteration of the loop involves constant time operations related to the dictionary, making the algorithm efficient overall. Now, combining the time complexity of the loop and the dictionary operations, we conclude that the total time complexity is O(n) for the loop multiplied by O(1) for the dictionary updates, resulting in an overall time complexity of O(n). Turning to space complexity, the primary factor is the dictionary frequency, which stores the frequency of each unique element in the array. In the worst-case scenario, all elements in nums are unique, so the dictionary would contain n key-value pairs. Each key-value pair requires constant space, so the space required by the dictionary is proportional to the number of unique elements, resulting in O(n) space. Additionally, we use a single integer variable, count, which requires O(1) space. Therefore, the overall space complexity of the solution is dominated by the dictionary, making it O(n). Let's examine the best, average, and worst cases for this solution. In the best case, all elements in nums are identical. Here, the dictionary will only store one key-value pair, but since we still need to iterate through the entire array, the time complexity remains O(n). In the average case, nums contains a mix of duplicate and unique values. The time complexity is still O(n), as the loop runs through the array exactly once, and the space complexity depends on the number of unique values stored in the dictionary. In the worst case, all elements in nums are unique. This means the dictionary will store n key-value pairs, with each unique element taking up constant space. Even in this scenario, the time complexity remains O(n), because the algorithm processes each element once. For comparison, a brute force approach would involve checking all possible pairs, I, j, or I less than j to determine if nums, I, equals nums, j. This requires two nested loops, with the outer loop running n times and the inner loop running up to n1 times, resulting in a time complexity of O(n squared). The brute force method has a space complexity of O(1), as it does not use additional data structures. The optimized solution significantly improves upon the brute force approach by leveraging a dictionary to track frequencies of elements. This eliminates the need for pairwise comparisons, reducing the time complexity from O(n squared to O(n). The trade-off is the use of extra space for the dictionary, which requires O(n) space in the worst case. To mathematically verify the big O time complexity, we note that the loop iterates n times, with each iteration performing dictionary operations that average O(1). This confirms the overall time complexity is O(n). The space complexity, on the other hand, is determined by the size of the dictionary, which depends on the number of unique elements in nums. In the worst case, the dictionary stores n key-value pairs, making the space complexity O(n). In conclusion, this optimized solution achieves linear time complexity while using additional space proportional to the number of unique elements, striking an effective balance between efficiency and resource usage. When solving this problem, there are a few common mistakes to watch out for. First, incorrect pair indexing is a frequent issue. Remember that valid pairs must satisfy the condition I less than j. If you count pairs without ensuring this, you'll violate the problem's constraints and produce incorrect results. To fix this, either explicitly check that I is less than j or structure your algorithm to naturally avoid invalid pairs. Another mistake is relying on nested loops for large inputs. While this brute force approach might work for small arrays, it results in n squared time complexity, which becomes inefficient for input sizes up to 10 to the power of 4. Instead, you can use a hash map to count occurrences and reduce the complexity to n. Lastly, off-by-one errors in frequency calculations can lead to incorrect results. For example, if you incorrectly compute the formula for combinations such as using n instead of n*(n1/2), you'll miscount the good pairs for elements with multiple occurrences. To avoid this, always use the correct formula, count*, count 1/2. Another common pitfall is skipping edge cases. For instance, if the array contains only one element or if all elements are unique, your solution might behave incorrectly or even result in runtime errors. To address this, make sure to test these edge cases explicitly, ensuring your solution doesn't count pairs when there are none. Additionally, using inefficient data structures can hinder performance. For example, storing frequencies in a list instead of a hash map may seem straightforward, but lists are slower for lookups, especially with larger inputs. Hash maps, on the other hand, provide average O(1) access time, making them the optimal choice for this task. From an interview perspective, this problem highlights an important pattern: counting pairs efficiently by leveraging frequency precomputation. Mastering this technique is crucial, as it forms the basis for solving many problems involving combinations. While brute force might be acceptable for small inputs, interviewers often expect you to optimize to n using hash maps, so it's important to be prepared to discuss the trade-offs between time and space complexity. Frequency counting is a particularly valuable skill, as it appears frequently in array and hashing problems. In addition, always make a point to explain how your solution handles edge cases, such as empty arrays, single-element arrays, or arrays with all unique elements. This demonstrates a thorough understanding of the problem and ensures your solution is robust. If you want to deepen your understanding of this problem, consider exploring related problems on LeetCode. For example, in LeetCode 1.2 Sum, you also use hash maps to efficiently track or count elements. LeetCode 560, subarray sum equals k, involves a similar optimization technique but uses prefix sums combined with hash maps. LeetCode 997, find the town judge, focuses on counting occurrences or relationships in arrays, while LeetCode 1090, largest values from labels, demonstrates how frequency counting can play a key role in solving the problem. These problems share underlying concepts that can help improve your problem-solving skills and prepare you for similar challenges. Finally, let's compare some alternative approaches to solving this problem. The brute force approach involves nested loops to check all pairs I, j for nums I equals nums j and I less than j. While this method is simple to implement, its n squared complexity makes it unsuitable for large inputs. A more efficient solution uses a hash map to count the frequency of each element in the array. For each unique element with frequency count, you compute the number of good pairs using the formula count*, count 1/2. This approach reduces the complexity to n, making it ideal for larger datasets, though it requires a solid understanding of hash map operations. Lastly, there's the sorting-based approach, where you sort the array and count consecutive duplicates to calculate good pairs. With a complexity of n log n, this method is less efficient than the hash map approach but may be easier to grasp for some. Each approach has its trade-offs, so it's important to choose the one that best fits the constraints and requirements of the problem. Great job making it to the end. To wrap up, we reviewed the core concepts of solving LeetCode problem number 1512 using an efficient hash map approach. Remember, practice is key to mastering these techniques. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!